Listen carefully. The Big Bang is taught as the moment everything began: space, time, and matter. But here's what scientists quietly admit. The Big Bang doesn't explain the beginning, it explains what happened after a beginning. And the evidence that revealed this is written into the oldest light in the universe. Most people imagine the Big Bang like a giant explosion, a tiny point suddenly bursting outward into empty space, creating everything in a single violent moment. That image feels natural, it's simple. And it's wrong. The Big Bang does not describe matter exploding into space. It describes space itself expanding. There was no empty room waiting to be filled. There was no outside space for the universe to explode into. Instead, space was already there, and it was stretching. A useful way to picture this is with a balloon. Imagine dots drawn on the surface of a balloon. As the balloon inflates, every dot moves away from every other dot. No dot is special, no dot is the center, and none of them are moving on their own. The surface itself is expanding. That's what the Big Bang describes. So, when scientists talk about the Big Bang, they are not talking about the creation of the universe from nothing. They are talking about a period when the universe was extremely hot, extremely dense, and rapidly expanding. And here's the part that usually gets left out. That description already assumes the universe exists, which means the Big Bang does not answer the most basic question we can ask. Why is there something instead of nothing? Now, let's take the story of the universe and rewind it. Not in a movie, in mathematics. Physicists take the equations that describe how the universe is expanding today, and they run those equations backward in time. As they do this, the universe becomes smaller, hotter, denser, galaxies move closer together, energy becomes more concentrated, space itself begins to shrink. But as scientists keep rewinding the equations, something strange happens. The math stops behaving, density shoots toward infinity, temperature shoots toward infinity, and time itself shrinks towards zero. This point is called a singularity. Now, that word sounds dramatic, but it's important to understand what it really means. In physics, infinities are not answers, they are warning signs. If you divide by zero on a calculator, the calculator doesn't reveal a hidden truth. It tells you the calculation no longer makes sense. The same thing happens here. When the equations produce infinities, physics is not describing reality anymore. It's telling us that the model has reached its limit. So when people say the universe began at a singularity, what they're really saying is this. This is as far back as our equations can go. The Big Bang does not describe the birth of the universe. It describes the moment when our mathematical tools stop working. Beyond that moment, physics goes silent. So if the Big Bang doesn't really explain the beginning, a natural question follows. Why didn't this bother scientists more? The answer is surprisingly simple, because the Big Bang kept working. It explained why galaxies are moving away from each other. It explained why the universe contains mostly hydrogen and helium. And it made one prediction that no other theory had ever dared to make. It predicted that the early universe should still be glowing, not with visible light, but with faint heat, stretched by expansion into microwaves. When scientists went looking for that glow, they found it, exactly where the theory said it should be. That discovery was a turning point, because once a theory starts predicting things correctly, scientists trust it, even if parts of it remain incomplete.
Spanning billions
At that
of light
moment,
years,
cosmology
these
faced a
filaments of
choice:
galaxies define
fix the
boundaries
beginning,
of the great
or
void.
use the theory to explain everything else first. Most chose the second option, not because they were careless, but because science is practical. If a model explains the data you can measure today, you keep using it. You don't throw it away just because it fails in an extreme situation you can't yet test. So the singularity problem was quietly set aside, not forgotten, just postponed. And for a long time, that decision seemed harmless, until better instruments began revealing details the theory wasn't prepared for. To understand why scientists began to worry, we need to talk about a very special kind of light. Not light from stars, not light from galaxies, but light from a time before either of those existed. Early in the universe's history, everything was so hot and dense that light could not move freely. Photons were constantly colliding with charged particles, trapped in a thick, glowing fog. The universe was opaque. But as space expanded, it cooled, and eventually, atoms formed for the first time. When that happened, light was suddenly released, and it has been traveling through the universe ever since. That ancient light still exists today. It's called the cosmic microwave background, or CMB, and it comes to us from every direction in the sky. This is important because it means the CMB is not coming from a particular place. It's not tied to a star or a galaxy or even a cluster of galaxies. It fills the universe uniformly. In simple terms, the CMB is the oldest picture of the universe we can observe, a snapshot of the universe when it was just a few 100,000 years old. Now, according to the Big Bang Theory, this picture should look very simple, almost perfectly smooth, almost perfectly random. Why? Because if the universe began in a hot, chaotic state, there should be no large-scale patterns left behind, no memory, no preferred directions, no structure bigger than tiny, random fluctuations. And for a while, that's exactly what scientists expected to see. But when satellites began mapping the CMB in greater and greater detail, something unexpected appeared. The picture wasn't completely smooth. It contained subtle patterns, not just small bumps, but features stretching across enormous regions of space. And that was the moment cosmologists realized the universe might be remembering something it was never supposed to remember. When scientists first noticed patterns in the cosmic microwave background, they were cautious. Very cautious. Because finding patterns where none should exist is one of the most dangerous situations in science. Sometimes patterns are real. Sometimes they're illusions created by bad data or human bias. So researchers asked the most obvious question first. Could these patterns be coming from our own galaxy? The Milky Way is full of dust, gas, and radiation that can interfere with measurements, so scientists carefully removed those signals from the data. Then they asked another question. Could the instruments be faulty? Different satellites used different detectors, different methods, and different scanning strategies. If the patterns were caused by an error, they should disappear when the data was processed in a new way. But they didn't. The same large-scale alignments kept appearing, not in one place, across the entire sky. Some of these features seemed to line up along a single direction, as if the universe itself had an axis. That idea was so uncomfortable that scientists gave it an unofficial nickname. They called it the axis of evil. Not because it sounds dramatic, but because it challenges a core assumption of cosmology, the assumption that the universe has no preferred direction. In a universe that began from chaos, every direction should be statistically equal, and yet the data suggested otherwise. Now, to be clear, this was not proof of a new theory. It was something more unsettling. It was evidence that the simplest story might be incomplete. And once that possibility exists, it refuses to go away. To deal with these early universe problems, physicists proposed an idea called inflation. Inflation says that in the first tiny fraction of a second after the Big Bang, the universe expanded incredibly fast, much faster than it does today. So fast that regions of space now separated by billions of light years were once close enough to interact. This idea solved several puzzles at once. It explained why distant parts of the universe have almost the same temperature. It explained why space looks smooth and nearly flat on large scales. And for a while, it seemed like inflation could rescue the Big Bang from its deepest problems. But inflation has a limit. Inflation stretches space. It smooths things out. What it does not do is erase information. A useful way to think about this is with a picture. Imagine you draw a small pattern on a rubber sheet. Now stretch the sheet. The pattern becomes larger and smoother, but it doesn't disappear. The information is still there, just spread out. The same logic applies to the universe. If the early universe contained large-scale correlations or directional patterns, inflation would stretch them. It would not destroy them. And that's exactly the problem. The strange alignments seen in the cosmic microwave background are not tiny defects. They appear on the largest possible scales, scales so large that inflation should not have been able to manufacture them out of randomness. This forced cosmologists into an uncomfortable position. Inflation explains how the universe became smooth, but it does not fully explain why certain large-scale features seem to remember a preferred direction. So inflation helps, but it does not close the case. Instead, it leaves behind a deeper question. If expansion can't erase these patterns, then they may have been present before expansion ever began. At this point, some physicists began to ask a question that once sounded impossible. What if the universe never truly began? What if the Big Bang was not the first moment of existence, but simply the earliest moment we can currently describe? To explore that idea, scientists turned to a field called quantum gravity. Quantum gravity tries to combine two very successful theories, quantum mechanics and general relativity, into a single framework. And when they did that, something interesting happened. The singularity began to disappear. In these models, space and time refuse to collapse into an infinite point. Instead of allowing density to rise forever, quantum effects introduce a limit, a stopping point. So, as the universe contracts and becomes denser, it doesn't reach infinity. It slows, it stabilizes, and then it reverses. This idea is called a bounce. In a bouncing universe, a previous universe collapses under its own gravity. Space shrinks, energy concentrates. But instead of ending in a singularity, the collapse transitions into expansion. The Big Bang becomes not a birth, but a rebound. In this picture, time does not start at the Big Bang. Time continues through it. There is no first moment, only a transition from one phase of the universe to another. And that changes everything. Because if the universe did not begin at the Big Bang, then before the Big Bang is no longer meaningless. It becomes a physical question, one that can, at least in principle, leave traces. Traces that might still exist today. If the universe passed through a bounce, then the Big Bang was not the beginning of everything. It was a transition. And that idea leads to a question that is both simple and unsettling. What existed before our universe? If a previous universe collapsed and rebounded, it would not simply vanish. It would leave something behind. Not stars, not galaxies, but conditions. The laws of physics we take for granted, gravity, space, time, energy, may not be fundamental rules of reality. They may be inherited traits, shaped by a universe that existed before ours. In that case, our universe is not a standalone event. It is part of a much longer story, one chapter in a sequence we are only beginning to glimpse. And here's the most unsettling part. If traces of a previous universe still exist, they would not appear as obvious objects. They would appear as subtle patterns, tiny asymmetries, faint correlations in the oldest light we can observe, which means the universe may still be carrying memories from before time as we know it began. We may already be looking at the evidence, we just don't fully understand how to read it yet. So the Big Bang may not mark the start of reality, it may mark the moment our universe became visible, and whatever came before it might still be shaping what happens now.